Let's see what happens. Yeah, there should be an a2b squared somewhere. Let's see. Okay, so let's see what happens. It's a good point, but we'll see. That was why we tried this. It didn't work. So we want to see if it comes up somehow. If you notice, right here, even though no one elementary reaction has that, I do have a product of a2b's here in this term. So it's possible that it comes about in another way, not by having a 2a2b. Okay, so let's look at the see if something cancels. Here I have a k3, k4, a2b, ab squared. Here I have a k3, k4, a2b, ab squared. This comes with a plus sign, this comes with a minus sign. They cancel. So this term cancels this term. Now let's look at the experimental facts. Experimental fact 1, number 3, which is the one I always seem to like the best, because it tells me information, is that the rate is not a function of AB. So let's notice this term has no ABs in it. This has no ABs, this has no ABs. So nothing's affected there. But this term does have an AB. So this tells me that the product of K2 and K4 is 0. One of them has to be 0. I don't know which one, but at least one is 0. So fact 3 tells me that the product K2, K4 equals 0. And that will kill off this term. And I've satisfied fact 3. Now, let's look at what I have here. As was just pointed out to us by the gentleman with the beer t-shirt, we have an a2b squared, as we needed to have an a2b squared. Now, let's notice what happens here. Okay, so we've satisfied fact 3. Let's look at fact 1. Fact 1 says at short times, the rate looks like it's first order. So at short times, how could I possibly get the rate being first order? Well, it would be first order if at short times, this term were negligible compared to this term. What does short term times mean? At short times, I have lots of A2B, and I've got very little A2 and very little AB, so I'm just starting the reaction. So short times means I've got a lot of A2B and very little A2 and AB. Well, if I have a lot of this and very little of this term is going to be negligible compared to that. So at short times, I have K3, K4, A2B squared over K3, A2B. The A2B's cancel. So at short times, can you see the blue? I have R of A2B equals minus 2K3. Well, the K3 A2B cancels. And I've just got a minus 2K1 A2B. Because this term is negligible compared with that, and the K3 A2B cancels, so all I'm left with is the minus 2 A1 A2B. So at short times, this is what I get, and this is indeed first order. So this agrees with fact 1. How about at long times? There are A2B. What happens at long times? At long times, I've used up A2B, very little of this, but I've got lots of these guys. So at long times, this term is tiny compared with this term. So this term becomes negligible, and I have minus K3, K1, K2 over A2B, A2B, A2. In other words, this goes like minus 2 K3, K1 over K2, A2B squared over A2. Well, that indeed is second order in A2B. So that agrees with fact 2. We're on a roll here. We've got facts 1, 2, and 3 that are doing well. Let's look at fact 4. Fact 4 says R A2B goes down as A2 goes up. long times A2 goes up. But it's not just a 1 over A2. It's not a proportionality. It's more complicated. Well, A2 is in the denominator, but it's not the only term in the denominator. So yes, this goes down as this goes up, but it's not a simple proportionality because I have another term here. The only thing I need to specify is we said the product of K4, K2 is 0. I need, for this to work out, I need K2 to be non-zero. So I need K2 to be not 0, but K4 to be 0. And then I satisfy all 4. So we've come up with a mechanism, actually. Ella came up with the mechanism that works. So we have a mechanism that works. Doesn't mean there aren't others, but at least we've succeeded. It only took us an hour. On the test, you're not going to have an hour for one question. Are there any questions on that?
So, in formulating all of these different test mechanisms, do you go through the reason behind why you have one different?
There a guess? Guessing. Okay. The reason for this was exactly the reason the gentleman in the beer t-shirt suggested. If we want a second order reaction, if we want a second order decay, the easiest way to get a second order decay is to have a stoichiometric coefficient of 2. Because then you automatically get an A2B squared. Automatically, without any work. That was the reasoning behind this guess.
So you're taking one condition.
Yeah, sure. I don't want to come up with a guess in a vacuum. I have experimental data. And this isn't a question of cheating. I'm trying to get the answer any way I can. So I use experimental data to come up with a guess. And I use exactly the reasoning of the gentleman in the beer t-shirt to get the reasoning. Unfortunately, this one didn't work. So then we said that doesn't work, so let's come up with another guess. No, the next guess was this won't work. So let's try another guess. I don't know, then I just came up, let's form one of the products as quickly as possible in the first step. Let's form one of the products in the first step and the other product in the second step. This one didn't work, so I'll just switch it around. Let's form A2 in the first step and AB in the second step.
There's no solid proof.
No need for excuse me, no need to say, now I'm going to ask a question. Just ask the question.
There's no solid proof that in the long time there is a...
These are gaseous reactions, not solids. There's no solid
concentration
proof.
of A2B is much bigger than, much lower than A2, because we have the equilibrium reaction.
Yes. Let me answer your question. In this problem, the reactions are equilibrium reactions, but we start out with a pure species. We start out, the reactant was just A2B. We start out with A2B. And the experimental facts tell you, remember, I can measure A2B, A2, and AB. I can measure those. When I say at long times, I'm telling you what I mean by that is the times are long enough that it turned out from the experiment that you had pretty good conversion. Not 100% conversion, but good conversion. So much of the A2B was used up. Yes, there doesn't, you can have an equilibrium where at long times they're all present in comparable concentrations. But I'm telling you, when I say a long time solution, what I'm telling you is experimentally in that case, there was a situation where at long times we have lots of 8 products. Now it doesn't mean we don't have very much reactant. And what I didn't fuss about was the size of K2 and K3. K2 and K3 are constants. When I say that this term is small compared with this term, I'm not saying that A2B is small compared with A2. I'm saying that K2A2 is large compared with K3A2B. So even if A2B is comparable in size to A2, I'm making a statement about the relative sizes of K2 and K3. And one thing that is true no matter what happens, no matter what the equilibrium conversion is that at the end of at equilibrium at long times, A2 is larger than it was initially. And A2B is smaller than it was initially. So what I'm making, I simplify the argument, and you're right to point it out. I simplified the argument until now by just saying, oh, there's a lot of this and not much of this. Really what I should have said is there's a lot more of this than I started with and a lot less of this than I started with. And I'm making a statement about the K2 and the K3 that K2 times the amount of this at long times is large compared with K3 times the amount of this at long times. So you're absolutely right. I was just being a bit sloppy.
In the long term, the K3
K2 and K3 don't change.
Yeah, I mean the product.
Yes.
K3 A to B is bigger than K2 in the long time. It's possible.
It would be
Yeah.
possible,
Yeah.
but that would not conform with the experimental evidence. Remember, the experimental evidence tells me the rates at certain concentrations. The Ks are unknown. The Ks are unknown a priori. So the question is, for this mechanism, does there exist a set of Ks that satisfies the experimental evidence? That's the question. The Ks are unknown. So it's possible, if the Ks weren't like that, it would disagree with experiment. But I don't know the Ks a priori. So what I'm saying is that if I find a set of Ks, such that K3 A2B at long times is small compared with K2 A2 at long times, given those concentrations. If I can find such a set of Ks, then this mechanism mirrors the dip. But yes, there's no guarantee. If somehow I had locked in a vault the real values of K2 and K3, and they didn't happen to do this, then that would contradict this mechanism, would disqualify this mechanism. But I don't have them locked in a vault. In fact, I use experimental data to infer what they are. And if I like this mechanism, then that implies, first of all, the Ks depend on the mechanism. If I change the mechanism, I redefine a new set of Ks. For this mechanism, this set of Ks, for this mechanism to agree with the data, it tells me that the Ks for this mechanism have to be such that those relationships hold.
And other assumptions.
I wouldn't say assumptions, implications. If this there's a big difference. Assumption is a wild guess. The implication says if this mechanism is to describe the data, then it must be the case that the Ks have this relationship. So if you want to be precise, what you would say at short times, you want A2B over A2 to be much greater than K2 over K3. Or if you like, K2 over K3 has to be much smaller than this. And at long times, short, and at long times, I want A2 over A2B long to be much greater than
K3 on K2.
A2 over
K3 on K2.
K3 over K2. Now note, these values at short times are very different from these values at long times. So this gives me inequalities that K2 over K3 have to satisfy. And these are experimental numbers at short time and very different experimental numbers at long time. And as long as I can find a K2 over K3 that work, as well as whatever else I need, then I'm okay. So you're absolutely right. I just didn't want to fuss that much at this point. That's the precise way of saying it.
Why were you allowed to do the course cancellations in white?
I'm sorry? We're allowed to do it because I have a term with a minus sign and the exact same term with a plus sign. So and they're being added, so I can always cancel +5 and -5. I'm always allowed to cancel.
Well, I'm seeing AB squared A to B.
AB squared A to B.
Oh,
It's a quick question.
Okay, no
Okay.
introductions.
Right.
Just ask the question. It's like
I got you.
Four scoring 7 years ago.
So when we do this, obviously there's potentially a lot of possible mechanisms, but I'm noticing
An infinite
an
number
infinite
of
amount. But in the situation that we have here, if we see that in a short term it's one power, and another term it's another power, couldn't we have eliminated this one here? We wouldn't know exactly what it was, but we can see that A2B is involved in both of these reactions, whereas over here it's not?
You know, if you have the insight to eliminate it immediately, go right ahead. I'm not saying you can or you can't.
But I was just wondering if there is some sort of pattern.
As you get more experience with this, you'll be able to look at mechanisms and maybe eliminate them. But the first time through in a class, I'm not going to use some insight that's not obvious. The second time through. Other questions? Okay, so let's go through and look at another situation. Let's look at a chain reaction. Here's the chain reaction. I have, okay, so I'm going to just give you a mechanism for chain reaction. And then we'll do a quick analysis of it. Chain reactions we know are non-elementary. So here we have Br2 goes to 2Br dot. Now this requires UV light. So we know chain reaction forms a dot is a free radical. Then I've got Br dot plus H2 goes to HBr plus H dot. And then I've got H dot plus Br2 goes to HBr plus Br dot. And the experimental facts. Experimental fact is that our friends the chemists spent a year in the lab determining that R of HBr was equal to some K1 times H2 Br2 to the 1/2 divided by some K2 plus HBr divided by Br2. So our buddies, the chemists, on the top floor of the Marshak building, determined. You know why the chemistry department is always on the top floor of the science building?
So
I'm not making this up.
the fumes could,
What's that?
if there's any fumes
No, because
released.
sometimes the chemists have a reaction that blows up, and this way they only blow off the roof. I'm not making that up. That's really why. I mean, today it's less common, but it has happened. Okay, so let's go ahead and do this. And now I'm going to label the reactions 1 plus, 1 minus, 2 plus, 2 minus, and 3. Because I don't like counting higher than 3. Okay, so we're interested in HBr, so let's write out our HBr. And who was I up to? Let me stop this. Okay, so HBr is involved in reaction in these reactions and this reaction. 2 plus, 2 minus, and 3. So I've got a K2 plus, a K2 minus, and a K3. Yes? So how about K2 plus? I didn't leave any room for the... Okay, so what goes here? Br dot and H2. And the stoichiometry? Good. 1 minus 0.
So for K2 minus, we have HBr minus, and stoichiometry is 0 minus 1.
Right. And
So for reaction 3, we have H dot, K3 times H dot times Br2.
And stoichiometry?
Stoichiometry is 1 minus 0.
good. Okay, that's HBr. Now, notice, unlike the previous cases, how many free radicals are always reactive intermediates? How many reactive intermediates do I have? And what are their names? H dot and Br dot. So I'm going to need RH dot and RBr dot. I'm going to need both of them. So let's go through and do it. H dot is involved in these two reactions and this reaction. So for H dot, I'm going to have a K2 plus Br dot H2 with some stoichiometry coefficient. And I'm going to have a K2 minus HBr H dot. And I'm going to have a K3 H dot Br2. And Br dot is involved in all 5 reactions. So I'm going to have a K1 plus, a K1 minus, a K2 plus, a K2 minus, and a K3. And let's just fill in what we know. H dot Br2. Here I'm going to have HBr, H dot, and here I'm going to have Br2, Br dot H2. Okay, so what's the stoichiometric coefficients for H dot? So notice I'm doing this a little quicker. Okay? 1 minus 0. Correct? And for this one, 0 minus 1. And for this one, 0 minus 1. Okay, and now for Br dot. I need to fill in this. What is, for a K1 plus, what do I have here? There's no dot, no. That's, no. Br2. And what's the stoichiometric coefficient? 0 minus 1. No,
No,
I'm sorry, no, sorry.
2 minus
Br2, Br dot. What? 2 minus 0. Right. Yes, and now K1, and now for 1 minus? What's goes here? Br dot to 2 power, yes. And what comes here? 0 minus 2. Good. Stoichiometry for Br dot in the 2 plus. This reaction for Br dot.
0 minus 1.
0 minus 1. The head of the arrow minus the tail of the arrow. 2 minus?
1 minus 0.
1 minus 0. And K3 for Br dot.
1 minus 0.
1 minus 0. Okay, so now we have the pseudo-steady state assumption on which species?
Br dot and H dot.
Good. And now what I'm going to do is, let's see how many equations, how many unknowns do I have? How many equations do I have? 3 equations. How many unknowns do I have?
2.
What are my unknowns?
H dot and the BR. No.
H dot, Dr dot, and
HB.
rate of H squared. So I have 3 unknowns, 3 equations. Is that good or bad? That's good. We can put a value judgment on it. That's good. Okay. So now, what I need to do, if I want to spend an hour doing algebra, is I can solve these 2 equations for H dot and Br dot, Br dot H dot, solve them, plug them in here, here, and here, and do a lot of algebra, make a lot of mistakes, and never get the answer. Or I can just use a little tricks with the algebra, and I can notice that here I have 3 terms, and let's notice that here I have, these have the same coefficient, these have the same coefficient, these have different coefficients, opposite coefficients. So if I add these 2, then at least this, or let me subtract these 2. If I subtract these 2, this cancels, and this adds. So the first thing I know is R of HBr is equal to twice K3 H dot Br2. So that's nice. That means I only have to plug in 1 place instead of in 3 places. Okay, now I need to solve for H2. So the first thing I can do is let me add these two equations. 0 plus 0 is 0. So this is R HBr plus 0 is this. But I also know that 0 plus 0 is 0 most of the time. So 0 plus 0, if I add these two, then notice these two terms cancel, these two terms cancel, and these two terms cancel. And the only thing left is these two terms. So this is equal to 2 times K1 plus Br2 minus K1 minus Br dot squared. So immediately, if this is 0, I can cancel this. And this tells me that Br dot is equal to K1 plus over K1 minus Br2 square root. That's a good sign. Square root. I like square roots. Just in the data. Okay, well that's nice. Now I still have to go back and solve for H dot, because I need to plug in here for H dot. Br dot's nice, but I need to plug in for H dot. So this equation has 3 terms, and this equation has 5 terms. Which one do you think is easier to plug into? Who was I up to? The one with 3 terms, yes. So I'm always looking for the easy way out. So and I know Br dot, so let's solve for H dot in terms of Br dot. Notice that these 2 terms have negative coefficient, this has a positive coefficient. So I can leave this term on the right, and K2 plus times, where am I? K2 plus times H2 Br dot. And I can bring these 2 terms to the other side and divide by the coefficient of H dot, which is K3 or K2 HBr plus K3 Br2. And for Br dot, and this is of course all H dot. And Br dot, I know what that is, so I'm going to plug in for Br dot. Br dot, I'm going to replace with root K1 plus over K1 minus root Br2. Is that clear? And now what I'm going to do, again, you don't have to copy the algebra. It's algebra. I'm going to plug this into this equation. Let's plug it in. So I've got RHBr is equal to 2K3 times H dot. H dot's all this. So let's put all the constants together. I've got this K2 plus root K1 plus over K1 minus times Br2 to the 1/2 divided by K2 K3 K2 HBr Br2. That's 2K3 H dot times Br2. Okay, so all I did is I plugged into here for H dot. And now what I'm going to do, because notice here I have a Br2 to the 3/2, here I have Br2 to the 1/2. I'm going to divide top and bottom by B, and I lost the term, plus K3 Br2. This is let's just copy that. Sorry, absolutely. Now I'm going to divide top and bottom by Br2. So if I divide the top by Br2 and the bottom by Br2, what am I left with? The Br2's cancel. The Br2's cancel. And let's compare these 2 forms. Here's my blue chalk. First, let's look at the dependence, and I lost an H2 somewhere. Where did I lose my H2? I'm sorry? It's an H dot. So I need the H2. Okay, so let's compare the dependencies, power dependencies. H2 to the first, H2 to the first, BR2 to the 1/2, BR2 to the 1/2. In the denominator, constant, constant. And H2 over BR2. HBR over BR2. HBR over BR2. So we have all the dependencies on the variables right. And all I have to do is notice that, first of all, let's notice that the way it's written here, there's no coefficient in front of HBR over BR2. To get that to work out, I divide top and bottom. This is by K2. This is a plus or minus now. K2 HBR. Okay, from this equation, K2 minus. This is a minus. I divide by K2 minus, K2 minus, K2 minus. And that will cancel this. And now what I have to notice is if I let K3 over K2 minus and capital K2, the constant here, and this whole quantity be capital K1, then the experimental curve and the experimental expression and the theoretical expression are identical. So that says that this mechanism does a good job. Okay, now, come. Do you see, let's take a step back. We went through the algebra at light and speed. I'm going to take a step backwards. And I want you to look at this mechanism. And I want you to tell me, is something missing in this mechanism? I'm not talking about the experimental fact. If you were writing down this mechanism, is there something that looks like it's missing here?
Termination step?
What termination steps?
Terminating the free radical. Yeah.
So tell me what the termination step should be.
Well, one free radical would, okay, BR would react with another BR or with another.
Well, that I have. Two BRs reacting gives me a BR2.
Okay, BR dot has to react with, let's say H dot or another BR dot.
It already reacting with the
okay.
BR dot I have. So I should have a BR dot reacting with an H dot to give me
HBR.
HBR. Any other steps then? Termination steps?
H dot.
I should also have H dot reacting with an H dot to give me H2. So I should detect some H2. The fact that these were not, in particular, that this reaction was not included, what does that tell you about the experiment? What does that tell you about the experiment? Remember, I can detect the stable species. It means there was so little hydrogen involved, I didn't even detect it. So what that means is that the chain is so long that the termination steps are fairly negligible. That is, the amount of HBr contributed by this reaction is much, much less than the amount of HBr contributed by these reactions. And the amount of hydrogen involved is so tiny it's hard to detect. So what that means is that every time the chain is initiated, it goes on many, 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 many steps before it terminates.
So we take into account those particular mechanisms because comparatively they're slower than when the radicals are involved. The BR dot plus H dot plus H dot.
These reactions happen so infrequently, they're not detected in an experiment. That's telling you hydrogen is not detected in an experiment. That's telling you that these happen so infrequently to a first approximation to try neglecting them. Then what we did is we went through the algebra by neglecting it, and we saw we cannot reproduce the experimental results very well. So that tells us it's okay in a first pass to neglect this. What I would like you to do for homework, in addition to everything on the sheet, is to redo this problem including these two reactions and see what changes. So you can call this K4 and K5. But all the rest of the homework's on the sheet. Because next time, please hand in the homework today. And if you have any questions, you're welcome to ask me. just it's time for me to let everyone else who doesn't have questions go. And we're going to stand outside so the next class can happen. Happy to answer questions.